Why can salt dissolve in water, while sand simply settles down? Let's understand mixtures and their separation in just 10 minutes.
Welcome to Teaching Science. Have you ever wondered exactly how we get those sweet white crystals of sugar from tall green sugarcane plants? Today, we are going to understand this entire chapter step by step so that you don't just memorize it, you actually understand it. All right, let's just dive right into this explainer. We're going to explore how these everyday miracles are actually made possible by the fascinating science of separating mixtures. I mean, think about it. From massive industrial processes like sugar production, all the way to life-saving medical tests that just need a few drops of blood, understanding how to separate mixtures is literally a game changer in our daily lives. So, what's really interesting here is the core difference in how we classify these things. Whenever we mix substances together, they generally fall into one of two buckets. First, we have a homogeneous mixture. Think of a solution of sugar and water. It's totally uniform, right? Your first sip is exactly as sweet as the last, and you simply cannot distinguish the individual parts. But then, you have a heterogeneous mixture, kind of like mixing sand into water. This one is decidedly not uniform, and you can visibly see all the different components floating around. Let's actually visualize this. Over on the left, that clear beaker, that represents a completely uniform solution. Everything is blended completely seamlessly. But then, look over on the right. You can clearly see a heterogeneous suspension. Those tiny particles of dirt or sand are totally distinct. And if you watch closely, they actually start settling at the very bottom over time. Okay, so an absolutely crucial point before we get into the deeper science is just getting our vocabulary straight. When we talk about solutions, we use two main terms, solute and solvent. Now, the solute is the stuff that gets dissolved, and the solvent is the substance that's actually doing the dissolving. For instance, back to our sugar water example, sugar is the solute that's being dissolved, and water is the solvent doing all the heavy lifting. Let's bring this to life with an experiment. Think about it. If we follow NCRT Activity 5.1 and literally divide our class into 3 groups, mixing 3 completely different substances into water, what do you think is going to happen when we shine a light through them? Imagine Group A has salt water, Group B has chalk powder mixed in water, and Group C has just a few drops of milk in water. And wow, this brilliantly illustrates a true solution. Look at Group A's beaker. As the laser passes through that salt water, the beam's path inside the liquid is completely invisible. Like, it's just not there. This happens because those dissolved salt particles are simply way too small to scatter the light. But now, observe Group C's milk and water mixture. The path of that pink laser light suddenly becomes highly visible inside the liquid. That means the particles in the milk mixture are actually large enough to scatter the beam of light as it passes through. This is a really beautiful scientific phenomenon, and it's known as the Tyndall effect. Because of this specific light scattering, we really need to clear up a common misconception. To our naked eye, milk looks perfectly uniform and homogeneous, pretty much exactly like a true solution. But scientifically, because its particles are large enough to scatter light and don't completely dissolve, it is actually a heterogeneous mixture called a colloid. So always remember this one. Milk is a colloid, absolutely not a true solution. So let's see how this actually builds into real-life applications. The exact amount of solute dissolved in a given amount of solvent or solution is what we call its concentration. And getting this exact proportion right is super important. Whether doctors are preparing oral rehydration solution, or ORS, to save a life, or farmers are mixing up pesticide sprays, you can't just mix random amounts together. Hitting that exact concentration is absolutely essential. We express this concentration mathematically in a few different ways, mostly just depending on what's most practical. Notice the nutritional info on these everyday products here. We use a mass-by-mass percentage for solid mixtures, like milk powders. But for liquids, like this bottle of white vinegar or maybe intravenous glucose in a hospital, it's just so much easier to measure volume, right? So for those, we use a mass-by-volume percentage. All right, let's solve a numerical together step by step just to really lock this in. In NCRT example 5.1, we're given 10 grams of salt, which is our solute, and it's dissolved in 90 grams of water, our solvent. So how do we find the mass-by-mass percentage of this specific solution? Here's the logical flow for this. First, we just add the solute and solvent masses together to find the total mass of the whole solution. That's 10 grams plus 90 grams, which equals 100 grams. Easy enough, right? Then our formula tells us to divide the mass of the solute by that total mass of the solution and multiply the whole thing by 100. So we substitute our values in 10 divided by 100 multiplied by 100.
I'll give you a quick thinking pause to do the math in your head.
Okay, let's check your answer. The two 100s cancel out perfectly, which means the concentration of this specific salt solution is exactly 10%. You nailed it. Section 1. Methods of separation. Unmixing mixtures. Let's get right into it. Now that we deeply understand what mixtures are and how to actually calculate their concentrations, let's explore how to unmix them. I mean, mixing is easy, but unmixing, that is where the real science happens. If you recall our curiosity question from the very beginning about sugarcane, well, here is your answer. If you take a highly saturated solution at a high temperature and let it cool down gradually, the pure solid separates out into this beautiful, regular geometric pattern. This technique is called crystallization, and it's exactly how industries get those pure sugar crystals straight from sugarcane juice. And depending on the mixture, we can use a bunch of other really fascinating techniques too. For example, we use distillation to separate completely mixed liquids based purely on their different boiling points. Then there's chromatography, which actually comes from the Greek word for writing with color, and we use that to separate mixtures based on how fast their different components move. We also have sublimation, which separates solids that turn straight into vapor without ever becoming a liquid. And finally, centrifugation. This uses incredibly rapid spinning to separate heavier particles from lighter ones, exactly like when they separate blood components in medical labs. Okay, let's do a quick 1-minute recap, just to seal all of this in your memory. We classified mixtures into uniform, homogeneous solutions, and non-uniform heterogeneous mixtures. We proved that colloids, like milk, actually scatter light via the Tyndall effect, even though they might look uniform to us. We calculated exact solution concentrations using the mass of the solute divided by the total mass of the solution times 100. And finally, we reviewed how awesome techniques like crystallization, distillation, and centrifugation are used to separate mixtures right back into their pure substances.
Before we go, I want you to think about this one thing. Since the air we breathe is just a massive homogeneous mixture of different gases, how in the world do you think scientists manage to separate out pure oxygen from it for hospitals? It's a giant puzzle, and we are going to uncover that exact mystery next time. That's all for today. Keep revising, and for more easy science explainers, subscribe to Teaching Science. If you found this explainer helpful, like it and hit the bell icon for notifications about new explainers. See you in the next chapter.